Hello and welcome to Serverless Data Processing on AWS, part of the AWS Innovate online conference. My name's Daniel Zoltak, and we're going to explore a real use case of IoT analytics using the Kinesis family of services. For many of you, this may be quite new, so we'll share a short demonstration of what's possible with AWS IoT and Amazon Kinesis. Now, we know that some of the techies tuned in today want to get under the hood, so we'll deep dive into the underlying reference architecture and implementation details. We hope that by the end of our time together, you'll have developed an appreciation of the AWS services required to build a serverless IoT analytics platform, be able to describe the role and functionality of Amazon Kinesis, Firehose, Streams, and Analytics. And finally, we hope you can walk away with an understanding of how to acquire, process, and store both raw and analyzed IoT data. So let's get started. The solution we're going to use as an example today is that of a number of environmental sensors connected over networks to a weather station. That weather station aggregates data from all the sensors, does some basic processing, and then forwards the data into AWS, where a serverless processing architecture is used to acquire, process, and present this data. We ran a bootcamp for 100 attendees at reInvent last year, where we had each attendee use an Intel Edison IoT device to act as the weather station. So we had 400 sensors and 100 weather stations, which were located all over the United States. All this data was fed into a global weather view, which you will see in a demo shortly, where the attendees could see the weather in real time. We made extensive use of the AWS IoT services and its features such as IoT rules, actions, and things. This part of the solution relies heavily on a number of serverless concepts. For storage, we use Amazon Aurora, Amazon S3, and Amazon Redshift. We use these services for different use cases, and we'll delve into the specifics later. AWS Lambda is used widely in the architecture to provide serverless zero administration compute functionality. The present phase heavily uses JavaScript both on the client and server side, hence the AWS JavaScript SDK is used. Security, authentication, and authorization are all key elements of this phase and are supported by the use of Amazon Cognito. The global weather view makes API calls to the global weather service, and this is facilitated by both Amazon API Gateway and AWS Lambda. When we lay out all the services we're going to use today, you can see that this is a broad architecture that's tightly aligned to AWS serverless concepts. What's interesting in this solution is that there are no virtual machines or containers visible nor referenced in our model. This means that when operating such a solution, there's no need to administer, manage, or scale any compute functionality yourself. Secondly, there's no need to scale any of the services. This means that it's not possible to either under-provision or over-provision capacity in the system. Now, let's take a look at all these services in action within the Global Weather View application from the reInvent Bootcamp. So, when our customers want to deliver a solution like the one we've just seen, they've generally asked us to help them in 4 key areas. Firstly, the ingestion of large volumes of high and low velocity data from large fleets of distributed IoT devices, the ability to perform real-time analytics on streaming data, remove the complexity of storing and processing large volumes of data, and finally, deliver a solution that doesn't require you to plan, scale, or manage any infrastructure using a pay-as-you-go cost model. It's easy to look at these challenges and ask yourself, why don't they just do it themselves? Well, there are some really good reasons customers look to a company like AWS to help them. Firstly, designing large-scale global systems capable of reliably ingesting data from billions of devices, generating trillions of messages in a distributed fashion is really hard. Secondly, the cost of that infrastructure is prohibitively expensive unless you have massive scale. And finally, the operational management and scale implications are a limiting factor that impede innovation and velocity. At AWS, we love solving hard problems, and more importantly, we like to deliver solutions that let our customers focus on their core business. The AWS services we're going to look at today take care of all the undifferentiated heavy lifting for you. This means that you can focus on the things that you are good at, and more importantly, on those activities that bring your customers real value. As with all good architecture, we start by building a generalized reference model. With all AWS architectures, we start with security, as this is our highest priority. In this model, security refers to everything from encryption, both at rest and in motion, to authenticate and authorization. We also need a network to transport the data end to end, and compute to process the data. Our reference model includes data sources. This may be IoT devices, such as a simple temperature monitor, or a complex device, such as a real-time blood glucose monitor unit, or even a purely software thing, which has been instrumented into a computer program. The beauty of a reference architecture is that we don't need to be overly concerned with the types of data sources. The data needs to be ingested into a large system. This generally needs to be done at scale and on a global basis. The data being ingested may be large but streamed at low velocity, or small and streamed at high velocity, or even random or bursty rates. We generally see the requirement for this data to be processed in either or both batch or real-time processing. For today, we call real-time processing anything that has a delay of less than 60 seconds, whilst batch processing refers to latencies greater than 60 seconds. Analytics is really the engine that processes either the batch or real-time data streams. It must support a standard query language without having to learn new programming languages or processing frameworks. Also, enable the users to gain actionable insights and respond to their business and customer needs promptly. This component of the architecture should take care of everything required to run queries and continuously scale automatically to match the volume and throughput rate of the incoming data. Of course, you're going to want to be able to store your data. This data may need to be accessed frequently by many different users who may demand that this data is fresh and represents a near real-time view of the data. Alternatively, some of this data may only need to be accessed infrequently, for example, used to run historical analytics in order to generate machine learning models for predictive analytics. That's quite a set of features and functionality that this reference model demands. When mapping the reference model to AWS services, the network element of this model refers to the Amazon Virtual Private Cloud, which enables you to launch AWS resources into a virtual network that you've defined. Amazon EC2 provides elastic compute capability. AWS IoT provides us the ability to deploy, manage, and communicate with billions of IoT-powered devices in a secure, managed way. Amazon Kinesis is a platform for streaming data on AWS, offering powerful services to make it easy to load and analyze streaming data. It also provides the ability to build custom streaming data applications for specialized needs. And finally, storage is facilitated by the Amazon suite of relational database services, such as Amazon Aurora, in combination with highly durable object store capabilities of Amazon S3. Of all the services in this reference model, we're only going to focus on those highlighted in red, and more specifically, the Kinesis family of services. Today, we know that the thing is actually our weather station, but in the outside world, the term IoT covers an expanding network of commonplace objects. These range from industrial machines to consumer goods that can gather information about the world around them, share that information between themselves or a central point, and provide data to make decisions to affect change in the real world. Hence, the Internet of Things, or IoT, and in particular the definition of a thing, is a very open-ended term covering connected things such as mobile devices right through to embedded devices. So, where does our thing or weather station fit into all of this today? Here's the AWS IoT framework. It consists of the message broker. This provides a secure mechanism for things and IoT applications to publish and receive messages from each other. The rules engine provides message processing and integration with other AWS services. The thing registry, this is something referred to or sometimes referred to as the device registry, which helps organize the resources associated with each thing. You register your thing and associate custom attributes with each thing. You can also associate certificates and client IDs with each thing to improve your ability to manage and troubleshoot your things. The Device Shadow service provides persistent representation of your thing in the cloud. The Device Gateway enables devices to securely and efficiently communicate with AWS IoT. The Security and Identity service provides shared responsibility for security in the AWS cloud. Your things must keep their credentials safe in order to send data securely to the message broker. The message broker and rules engine uses AWS security features to send data securely to devices or other AWS services. This is where we introduce the concept of a device shadow. This is effectively a JSON document used to store and retrieve current state information for all things. It allows us to persist state of the device during intermittent connections. As with all AWS architectures, we stress that you should design for failure. With the device shadow, we've taken care of the undifferentiated heavy lifting should your thing lose connectivity. A thing may lose connectivity for a number of reasons. Control code may want to conserve battery life and shut down the device. The device itself may be stable, but the network it relies on to send messages may be unstable or even unavailable for periods of time. With AWS IoT, you can create a persistent virtual version or shadow of each device that includes the device's latest state, so the application or other devices can read messages and interact with the device. The device shadows persist the last reported state and desired future state of each device, even when the device is offline. You can retrieve the latest reported state of a device or set a desired future state through the API or using the rules engine. In this way, a device state can change by request, even if the device is not connected to the network. We just mentioned the fact that AWS IoT service can interact with other services. This is made possible by using the AWS IoT rules engine. The AWS IoT's rules engine provides message processing and integration with other AWS services. You can use a SQL-like query to select data from message payloads, process the data, and send the data to other services such as Amazon S3, Amazon DynamoDB, and AWS Lambda. You can also use the message broker to republish messages to other subscribers. The security ecosystem surrounding and integrated into AWS IoT is extremely rich, ranging from integration with AWS Identity and Access Management, IAM, and certificate management for IoT things and devices. The AWS IoT message broker authenticates and authorizes all actions in your account. The message broker is responsible for authenticating your devices securely, ingesting device data, and adhering to the access permission you have placed on devices using policies. For the Processing IoT Data Using Serverless Architectures Bootcamp, we came up with a scenario where we aggregated weather data for a global weather service. Each student received an Intel Edison which represented a remote weather station located in a city within a state in the United States. Each weather station was the aggregation point for temperature, wind, vibration, and rain sensor data. We had the challenge of acquiring the sensor data from the remote weather stations, processing and analyzing the data, and presenting the data. This is all done following a serverless architecture approach. Stepping through the overall data flow from the weather station to the web application. First, the data is sent to the AWS IoT service, then processed and streamed using Lambda and Kinesis into the data stores. Then, the data is accessed via a single-page web application that leverages Cognito for authentication and authorization, an API gateway to query the data from the Amazon Aurora database using a Lambda function. Today, we'll be focusing in on the acquisition and processing of the data. Let's first look at the acquire section. Sensor data is sent from the 4 sensors and aggregated on the weather station using the MQTT protocol. The weather station was preloaded with a certificate that identifies the device and that authenticates the device with the IoT device gateway. Data is then securely sent to the IoT device gateway over specific topics. The topics the device can publish to are specifically allowed by using an IoT policy. The IoT rule transforms and republishes the data using an IoT action to the Amazon SNS topic. Now, let's focus in on the processing section. The IoT action sends the sensor records to Amazon SNS. We can see SNS is the bridge between the acquisition and processing sections, where the Lambda function is subscribed to the SNS topic. Now, let's look at the IoT rule setup. Here's the topic structure. As you can see, it's made up of 6 segments consisting of a prefix, state, city, station ID, sensor type, and the sensor ID. Here is the SQL-like query that transforms the incoming topic segments and payload into an output payload. As you can see, we have extracted the sensor ID, station ID, and sensor type using the topic function from the corresponding topic segments. We've also extracted the sensor timestamp and sensor values from the payload and typecasted these values. Here's the incoming payload. Now let's compare it with the transformed and enriched payload containing the additional sensor metadata. We've leveraged an SNS topic so we can fan out the data. SNS also gives us the ability to invoke multiple Lambda functions to process the data for other use cases or send the data across to another AWS account or third party. Now let's take a look at the Lambda function used for processing the data. The IoT loader function injects the sensor records into a Kinesis stream and Firehose delivery stream. The RDS loader uses a Lambda trigger that polls the Kinesis stream and processes the available records. The function sources sensor records from the Kinesis streams that contain the raw sensor data and the summarized sensor data. The function then inserts these records into the Aurora database. Now let's review where the Kinesis family of services is being used. The raw sensor data from the IoT device gateway is being loaded into a Kinesis stream for real-time processing. Raw sensor data is also being loaded into a Kinesis Firehose delivery stream that is batch loading data into S3 and Redshift every minute. The Firehose delivery stream is the input stream for the Kinesis Analytics application. The Kinesis Analytics applications summarize sensor data for each sensor, where the new record is put into an output Kinesis stream. So let's quickly recap. Since the launch of Amazon Kinesis in 2013, the ecosystem evolved and we introduced Kinesis Firehose and Kinesis Analytics. So what are the characteristics of each service? A Kinesis stream is targeted to low latency streaming and ingestion at scale. Kinesis streams can go from tens of messages per second to hundreds of thousands. Kinesis Analytics is for streaming analytics in near real time and automatically scales compute resources based on the incoming message rate. Kinesis Firehose is for batch data delivery and is buffered based on time and size, and then is batch loaded into supported data stores. Now let's contrast Kinesis Firehose versus Kinesis Streams. Kinesis Streams is for the use case for custom processing per incoming record and can be delivered and processed with sub 1 second latency. A stream can be processed with EC2, Lambda, or on-premises compute using custom applications. Kinesis Firehose is for the use case that require zero administration, where a data latency of 60 seconds or higher can be tolerated. The data is batch loaded natively into S3, Redshift, and/or Amazon Elasticsearch. Building a real-time application with Kinesis Analytics is easy. There are three major components of a streaming application. You can connect an input stream, then write SQL code to process the incoming data, and finally connect an output stream enabling the results to be continually delivered. Inputs include Kinesis streams and Firehose. Standard SQL code consists of one or more SQL queries which make up the application. As we've already seen in the processing architecture, the input stream to the Kinesis Analytics application will be the Firehose delivery stream. The SQL will average, count, and calculate the minimum and maximum temperature for each sensor over a 1-minute window, generate a new record at the end of every minute, and emit it to the output stream. Going back to the Global Weather View application, where did we obtain all the data? For each sensor, the current sensor value was obtained from the IoT gateway using MQTT over a WebSockets connection. The average, minimum, and maximum sensor values were queried via API gateway. The short-term trending graph was obtained via the IoT gateway using MQTT over a WebSockets connection. Sensor performance metrics and the long-term trending graph data was obtained via API gateway. To understand how the Kinesis application works, let's take a closer look at the SQL query. First, we create the in-application stream with all the columns. Then, we insert data into the output stream using a pump that selects the records from the input stream. The console will show the results of the query being delivered in real time. Here's an example of an emitted payload from the reInvent bootcamp. Bold represents the values that were generated by the Kinesis Analytics application. Now, let's look at the data stores. We're using Amazon Aurora to store raw, deduplicated, and summarized data for historical querying via API gateway. For the use case in this architecture, imagine scaling from thousands to millions of API requests per minute. At an API level, caching has very little benefit when disparate historical weather data is being queried. To meet this specific data access requirement, Aurora is a very cost-effective solution as it allows reads to be scaled by adding additional read replicas. The read replicas can be accessed through a single reader endpoint, which is fully managed and updated dynamically by Amazon Aurora, simplifying application configuration. For reporting and analytics purposes, and to query large volumes of data fast, we're using Amazon Redshift. As an example, we could correlate weather data against historical retail shopping trends. Redshift, being a cost-effective columnar data warehouse solution, provides the capability to query large amounts of data fast. The data can be queried using native PostgreSQL or analytics and BI tools to explore and expose data trends and feed to machine learning to build models for predictive analytics. So, putting all the storage solutions together, we've created a data lake. S3 is fully managed, low cost, secure, and the foundation to the data lake, where we store raw sensor data for warm access. As the data ages, we can set policies to lifecycle to infrequently access S3, Glacier, or finally delete the data. S3 is natively supported by frameworks such as Spark, Hive, and Presto, so we can use the Elastic MapReduce service to easily load and query the data, allowing us to find answers to questions we didn't initially know to ask when we first acquired the data. Redshift is optimized for data warehousing and analytics, allow querying of large amounts of data fast. We can easily increase performance by scaling Redshift using an API call. Aurora is a cost-effective solution for querying data at scale. The underlying storage is scalable, fault-tolerant, and is leveraged by the Aurora database engine to handle high-volume, high-throughput queries at scale. So, IoT with real-time analytics provides meaningful information, not just data. Coupled with serverless components, we can scale without intervention or additional operational cost. This removes management and scaling overhead to help accelerate innovation. Well, that's it for this session. We hope you found it interesting. Do provide us with your feedback and let us know how we can improve the event experience for you in the future. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Attend our instructor-led classes with qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. And then validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. Finally, I'd like to thank you for attending today and sticking it out until the very end of the presentation. I also want to wish you good luck in leveraging serverless data processing on AWS to simplify scaling and operating your data processing solutions. Thank you.